Hey guys, welcome to 10.1a. This is the first lesson of our series and sequences unit. And today is just an introduction. One thing to keep in mind is today we're not using any formulas. These are patterns and we're just looking for the recognition of patterns, the different ways that these series and sequences can be formed. So just keep that in mind as we go along with this unit. It's going to get much more structured with the formulas that we use. So the first example here is just the definition of a sequence. It's a pattern of numbers that is either finite or infinite. It is an ordered list. So some examples here are 1, 2, 3, 4. Now notice we have like the little dots here. That means that it's going to continue on beyond those forever and ever. So this would be an example of an infinite series because it continues on. And then this one, 6, negative 12, 24, negative 48, that would be finite. Okay. And finite just means it has an ending number or an ending point. Infinite continues forever. Continues on forever, continues without end. So this one is an example of the infinite. This one is an example of the finite. And the three little dots are what tells us that. Okay, the next part here, when you're looking at a sequence, we call these terms. Okay, so n is where the number is in the sequence. So if you look at this first pattern, this would be n equals 1. This would be n equals 2, n equals 3. And so forth, because those are the terms. So 2 is the first term in the sequence. A of n is which term in the sequence. An example, a of 1 is the first term in the sequence. And then you would have the next part. A of n minus 1 is the previous term. So that's just looking back at the term before the last one. So let's continue on. 4, 5, 6. So here we have 6 different terms. And then the general rule for generating any term is a of n equals, and then you would have your rule. So an example of this would be a of n equals 2 times n. So whatever the n is, whichever part of the sequence we're looking at the first one, then it would be, so let's say we did a of 1. Then it would be 2 times 1, which would equal 2. Or something like you could do a of 5. So that would be 2 times 5 equals 10. So 10 would be the 5th term in that sequence. All right, now writing terms, we want to write the first 6 terms of this sequence. So when you're writing it out, a of 1, we would just notice that this is the very first term, so we're going to plug in 1. So it's 5 minus 1, which equals 4. We would just continue on. A of 2 is 5 minus 2, which would equal 3. A of 3, 5 minus 3, which would equal 2. And we just continue on. And as you notice, it's going down by 1 each time. So the next one is going to be 1, 0, and negative 1. So that would be the first 6 terms for that one. Continuing on to the other side, this one, now notice n is in the exponent. So a of 1 is going to be 5 to the first, which is just 5. A of 2 is 5 squared, which is 25, and we're just plugging in the number. A of 3 is 5 cubed, so that's 125. And you kind of get the pattern, so I'm just going to write the numbers down. Then we would get 625. A of 5 would be 3,125. Then A of 6 would be 15,625. And then we would have all the numbers in that sequence. So if you wanted to line it up, you would write it as 5, 25, 125, 625, 3,125, and 15,625. Okay, a couple more examples here just to kind of familiarize with how the patterns can look. So this one we have 5 and then we're adding n squared. So there's 2 different operations going on here. This one, it's probably better to write it out. A of 1 would be 5 plus 1 squared. 5 plus 1 would be 6. A of 2 would be 5 plus 2 squared. And this is where you have to remember the order of operations. So we would do 2 squared first, which is 4. 4 plus 5 is 9. Okay, and then you get 5 plus 3 squared. 3 squared is 9. 9 plus 5 is 14. Now notice, we're just going up by 5 each time. So if you recognize that, you can go ahead and... Actually, we are not going up by 5 each time. I lied. It's not a consistent pattern because we're going from plus 3 to plus 5 here. So we wouldn't be able to jump that step. We would want to continue on. So then we would have 5 plus 4 squared. 4 squared is 16. 16 plus 5 is 21. And then we would have 8 to the 5th. 5 plus 5 squared. So 5 squared would be 25. 25 plus 5 is 30. And then the very last one here, 5 plus 6 squared. 36 plus 5 is 41. Now we would have all of the first 6 terms. Now this next one here, you have to be careful. This is called a recursive formula because what it does is it requires you to understand what the very first term in the sequence is. So that's given for us. But to find a of 2, you have to look back. Remember this a of n minus 1, that's just the previous term. So a of 2, the previous term, is going to be 4 plus 3, which is 7. And then a of 3, now that is the new previous term. So it's going to be 7 plus 3, which is 10, and so forth. And we just continue with this pattern. So a of 4 would be, not 7. 10 plus 3, which is 13. A of 5 would be 13 plus 3, which is 16. Notice every time we're going back to, it requires part of the previous answer. And then a of 6 would be 16 plus 3, which is 19. Right, the general rule of the sequence. So this is the hardest part of the lesson, is just identifying some of these rules and patterns. They can be fun, but they can also be very challenging. So we just have a couple to go through here. For each sequence, describe the pattern, write the next term, and then write a rule for the nth term. So the pattern is, look at the fact that we have fractions here. Another thing that hopefully jumps out to you is that we have 2 on top every time. Okay, that is consistent with each new term. The next thing you have to remember is look at the fact that this is 5, and then this is 5 squared, or 25. This is 125, but they're going up by multiples of 5. So we're kind of like multiplying the bottom by a factor of 5. So the pattern here is going to be 2 over... Then I'm just going to make a note that it's a multiple of 5. But what's happening here is, so the base is 5. Hopefully you recognize this is like an exponent. That's what's going on here. So we're going to have an exponent for the 5. And then the next term would be 2 over 3,125 because it would be 5 to the next power. Remember that each of these, they count by 1. So this is n equals 1, this is n equals 2, n equals 3, n equals 4. So we have to have n in our final rule. And how this one's going to look is a of n, we do that every time. 2 is on top every time, so there's nothing's being affected by the n there. It's actually 5 to the nth power. Because if we think about the first series, or the first sequence, or first part of it, 5 to the first would be 5 on the bottom. 5 squared would give us the 25. 5 cubed would give us the 125. So it does fit the pattern that we have here. The next one, now here you have to look and see if there's any consistent pattern that's changing. With this one, we're going up by 2 each time. So we are adding 2. And then the next term, as you can guess, is going to be 11. We would just add 2 to the previous term. Now the rule for this one is a little bit different though, because we need to incorporate the n value. So this was 1, 2, 3, 4. So if we add 2 to the n value, so 1 plus 2, that would give us 3. But the problem is, if our n value for the second one, 2 plus 2 does not equal 5. That's not true. So we have to do something different. The trick to this one is to recognize that we are actually going to be multiplying the n value by 2 and then adding 1. So it is 2n plus 1 is the pattern. Okay, so we multiply the n value. So if we did a of, let's see if this works. So 11 would have been the fifth term. 2 times 5 plus 1. 2 times 5 is 10. Add 1. We do, in fact, get 11. Couple more to go here. For each sequence, describe the pattern, write the next term, and write a rule. Again, with this one, look and notice, see if you can find any consistent parts to each term. So we have 3 halves, 3, 9 halves, and then 6. Now notice we're alternating between fractions and whole numbers. That's kind of an indication that maybe we're working with fractions. So with this one, remember we can always rewrite whole numbers as fractions. So we have a denominator of 2 both times here. So let's try writing 3 and 6 with denominators of 2. So we would think of it as 3 over 1 times 2 over 2. So we're just going to rewrite this as 6 over 2. And then this one, same idea. We would multiply the top and bottom by 2 and we would get 12 over 2. Now hopefully you see that we go from 3 halves to 6 halves to 9 halves to 12 halves. So the pattern is we are actually going up, we are multiplying by 3 on the top. So 3 times the n value over 2. And the next term is going to be 15 over 2. So the rule for this one is a of n equals 3n divided by 2, because we have 2 every time. So whatever the n value is, you're basically just multiplying that by 3 halves. All right, one more to go here. This one we are changing. We have fractions every time, so we don't need to rewrite anything. But notice on the top of this first one here, 1, 8, 27, and 64, hopefully those are jumping out at you. Those are all perfect cubes. So we have cubes on the top, and then the bottom, looks like we're just adding 1 to get to the next number. So plus 1. So the next term, if we think about this as being perfect cubes, so the next perfect cube would be 125, and then add 1 to the previous number 5, and you would get 6. So the rule for this one is a of n equals, now we need to remember this is 1, 2, 3, 4. So how do we incorporate the n in this process? Well, we actually have to do it 2 different ways. On the bottom, it's actually easier. It's just going to be the n value plus 1. So if we want to get 1 to 2, we can add 1, 2 to 3, you can add 1, and so forth. The top, however, that one's a little different because we have 1, 8, 27, and 64. So we are cubing each time, and the first number you would cube is 1, and then the second number you would cube is 2 and 3. So it's actually just the nth term cubed. And that would be our rule.